Good morning, everyone. It's just about 9 a.m. here. Thank you for dialing into Coffee with Clusterone. I'm Patricia. I am the community lead at Clusterone, and we're really stoked that you're here for today's webinar. Coffee with Clusterone has been specifically crafted for developers, data scientists, and deep learning aficionados. So you can expect to find here information and education around deep learning. Today, we are excited to have Malo Marek, who is our co-founder of Clusterone and our product strategist. And then we have our CEO and co-founder, Mohsen Hejrati, who's going to talk to us about how to tune neural networks. We welcome all of your questions to come in the chat box. We will answer them at the end. And you may ping me directly on chat if you have any specific questions that are not related to our webinar today. And now we're going to hand it over to Malo to tell us a little bit more. Thank you for coming.
Good morning, everybody. I'm very excited to be here. So I'll start with a very brief presentation about Clusterone and what we do, and then hand it off to Mohsen, who will talk about how to tune deep neural networks. So Clusterone was created with the goal of enabling data scientists and deep learning scientists and engineers to scale their AI development and to make the development of models at scale easier and more efficient from a performance and cost perspective. So we were founded in 2016, and we launched in the summer of 2017 before raising our seed round this December 2017 from the Allen Institute for Artificial Intelligence in Seattle. And we now have a global presence in Seattle, the Valley, Poland, and Canada. So Clusterone was built to accelerate research by enabling data scientists to take advantage of scalability, distributed training, and generally speaking, speed up model development. Our platform is zero DevOps so that deep learning scientists can focus on modeling and not on setup. And we are striving to make it infrastructure agnostic, meaning it can run on any cloud or on any infrastructure, on-premise or hybrid, so that you have the power to choose the infrastructure that fits the best your need in terms of cost or performance. So the way our platform works is it runs on any infrastructure. It can connect to any source of storage and any artifacts for code such as GitHub or Quay or Docker Hub. And then Clusterone manages all the OS layers, so the Kubernetes, the firewalling, account management, access control, workflows, etc. So that as a data scientist, you don't need to worry about all the orchestration and cluster management part. And it gives you access to that powerful, very scalable platform through an API or a CLI or a matrix. And so on top of that, you can see all your tools, TensorFlow, PyTorch, any machine learning frameworks, and all the tools that you expect. So Jupyter Notebooks, TensorBoard, so that it becomes very easy and frictionless to run deep learning jobs at large scale. We have customers across several verticals, big and small. And a good example of that is Roche, where we enable their deep learning team to run very large-scale distributed training on terabytes of genomics data. And now I hand it over to Mohsen, who will talk about how to tune deep neural networks.
Good morning, everyone. Good morning. I'm Mohsen Hejrati, co-founder and CEO of Clusterone. In past life, I've been a machine learning scientist and spent many years training machine learning models and tuning their performance for various applications. Previous job, I have been at Google self-driving car project, training neural networks for the vision part of the car. And I think this subject is quite interesting because there are a lot of aspects to this that are usually dismissed, and there's a systematic way to look at it, and I hope that this can be a nice presentation for you so that you have a framework to think about what it means to tune neural networks and how to approach it in a systematic way. You can always get much better performance if you find better ways to tune neural networks. So always, when you are thinking about all the mission critical applications, then a few percentage point can lead to huge savings in cost down the line, or big competitive advantage. So that's why I thought this is an interesting topic, and I hope you find it useful as well. This presentation comes in 3 parts. So today is the part 1 of the presentation, where I'll try to build the foundation and framework to think about the tuning of neural networks and neural network systems. And then in the part 2 and part 3, we'll be more hands-on, and we'll get to do actual tuning in much more depth. So feel free to ask questions in the Q&A, and we'll get to that. So my presentation is going to be about 25 to 30 minutes. And then I really like to have time to answer questions. You can also reach out to me directly on my email or Twitter if there is anything I can help with. So the outline of this talk, first of all, we'll go through like a 1-minute definition of a neural network, not spending too much time on that. And then I like to talk about the neural network system, and then how to tune neural networks, and then practical examples, which will be parts of the next presentations. So a neural network, a lot of us already know. So it's composed of neurons, which are elements that do some basic calculation, and they have some inputs and some function inside, and then they produce output that can be fed into other neurons. And this very simple structure can be extremely powerful if done in the right way. So if you connect these neurons in a way like this, you can solve some classification problem or regression problem. And so the beauty of this is that it comes from very simple principles, but can become extremely powerful. So this is a multi-layer perceptron model, very basic. It has some input layer and output layer. And for the purposes of this talk, I'm going to just stick to this. But the principles will be applied to generally every other neural network. And so there are 2 phases in building and using neural networks. The first step is training. And training requires some data pre-processing, some data generation and labeling, and then data pre-processing. And that data will be fed into the input layer of our neural network. We do a forward pass, which means using the existing weights in the neural network and the data, we compute the output layer, and then we compute the error on the output layer, and then we back propagate that error to find the updates to the weights of the neural network. And then we apply those weights using some optimization technique, and then we update the neural network. We go to the next batch of the data. We do the same. Ideally, this neural network will converge to a set of weights that can solve our problem or minimize the error that we expect. And after that, during the inference, We do the same for data and pre-processing, and then we feed that data just to the forward pass, and then the output is our goal, and then we do some post-processing to use that output into some product or some end use case. So that is very high level about neural network, but then in reality, when we are going to use neural network for real life applications, we are dealing with neural network systems. And what is a neural network system? It consists of not only the algorithm and the data, but also you have to think about the storage, the compute, and the training resources required. So all of a sudden, when you're going from the theory to application, things become more complicated. Although there are a lot of efforts, with the open source tools and with the hardware that is available to us to make this simpler. Still, if you have a solid understanding of the whole system, you will be able to tune these much better and get better output. So what do we need to know about a neural network system? Usually the data is stored on some storage, and that can be a local storage on a desktop or laptop or on a server, a network storage, or a streaming source of data. And each of these have their own limitation. For instance, a local storage can hold up onto a certain amount. So the largest local storage you can get cannot reach beyond a couple of terabytes. But the network storages can be much larger, but then it comes at the cost of performance and bandwidth and latency. So then you have to think about how would that affect your performance during training and inference. And the same for streaming. The pre-processing is very flexible part of the neural network. So different use cases require different pre-processing steps, but usually it consists of decoding. If you have images or audio, you have to decode it to some matrix format. Then you transform that. If there are images, you may want to normalize them, or audio the same. And then you augment that data. This is a very important technique for regularization and generating more data for your neural network algorithms. And then you batch that data and feed it into your training pipeline. So this in itself, the pre-processing, is a very complicated piece that has all sorts of relationships with your storage and compute, and this can be optimized further. And then the training itself, it's mostly compute heavy, so you require to do a lot of calculations, matrix multiplications, and so on and so forth. And this usually happens either on CPU, GPU, and nowadays you'll hear a lot more about TPUs and FPGAs and custom chips for training neural networks. And the general things that can limit the training performance is your compute capacity and your memory and network bandwidth and latency, in case you are dealing with network storage or if you are trying to train models in a distributed way. So we'll get to all the details in the future presentations, but this is just to build the foundation and understand that when we are talking about tuning neural network systems, what we are talking about. So goal of tuning is really finding better models faster and cheaper. So what I mean by better models is models with higher test accuracy and lower memory and lower compute requirements. And usually people overlook the faster and cheaper part. So this is usually the case for academia, but our focus is mostly on finding better models. And by better models, we usually focus on just finding higher test accuracy models. And that is where, that is what we call hyperparameter tuning, meaning, you know, finding the parameters that will increase the chance of, you know, finding better model accuracy. So in this, in part one of the presentation, I'll overview this, finding better models, and mostly focus on finding a systematic way of finding better hyperparameters, because there's so many of them, and it's good to know how to start. And then in the future presentations, we will get to more of the systems level optimization and all the research that's going on into that space. So let's get to that. So really, when we are talking about finding better models, it's very important to know what is the definition of the better model. And the definition of the better model is to have lowest error, expected error on the test set. And so if you look at the expected error on the test set, you can do the math and divide it to bias and the variance. And this is what leads to the bias variance trade-off, where you can have many different models, and these models can be complex or simple. And depending on your data, finding the right model is the most important part. And you want to find models that has the right trade-off between the bias and variance. So for instance, a very simple model can have large bias, but low variance. And a very complex model can have a large variance but low bias, and none of these are ideal. So so on the plot on the right side here, you can see that the total error, as your model complexity grows, the total error first goes down and then goes up again, because your bias goes down as the model complexity grows. In general, your bias always goes down, and as the model complexity goes increases, your variance goes up. And similarly, you can observe that as your model complexity grows, your training error goes down, but your test error goes up. So always our training error, if we are finding the right optimization algorithm, our training error goes down as we increase the model complexity, but what we call this is overfitting. So ideal scenario is finding the right model complexity for our problem, and that is what the goal of hyperparameter tuning is all about. So up to this point, we just defined what do we want to achieve by doing this part of the tuning, and I think the approach, the systematic approach, is a coordinate descent approach. So we have 3 different coordinates to optimize for. We have model complexity, which in the case of neural networks is the number of layers, number of nodes per layer, complexity of each node, and so on and so forth. So these are the complexity inside the representation that we can adjust, we can increase or decrease. On the other side, the other coordinate that we can optimize in is the task complexity. So imagine ImageNet challenge, where we have 1,000 classes and millions of images. So this is a very complex task. It has many data points, it has many labels, and size of each data point is big, it's an image, and so on. But compared to that, you can think of MNIST, which has a couple of thousand data points, small images, just black and white, and also just 10 classes. So task complexity can grow, and then that's one other direction. And the coordinate descent approach is actually pretty simple. When you want to do tuning for a neural network model, if you want to do hyperparameter tuning, you should start with a very, very simple task and model. So if your end goal is a very complex task, for instance, ImageNet, first start by a simpler version of that. Let's just choose 2 categories inside ImageNet and use 10 or 100 data points per category. Let's say we want to solve ImageNet. We'll pick cats and dogs, and we pick 10 or 100 instances of cat images and dog images, and we restrict our problem to that small, simpler task. Okay, so we start with a very simple task and a simple model, and then we start with a simple model, but then the first step is to increase our model complexity little by little, and find an optimization that trains that model to solve the current task. So if we are trying to classify cats and dogs, we have to find a neural network model that can at least classify 10 or 100 cats from dogs. If we are not able to find anything that solves this, any optimization or a neural network, then we are probably not on the right track for solving the more complex task. And when we get to that point, we can increase the task complexity a little bit. So we can increase our data points or increase the number of classes, and then go to the first step and then increase the model complexity. So if you look at the history of computer vision, people started with very, very simple tasks like MNIST, the optical character recognition task, or Caltech 101 dataset, or Pascal dataset with 20 classes. And then we got to the point where we had much more data, but even then we can't solve all that in one shot. So the systematic approaches take the first coordinate, which is model complexity, increase this a little bit, find that optimal point that solve that simplified task, increase the task complexity, go back and move forward. This allows us to be able to debug our models much better, have understanding, and have much faster iteration time. So going back to that, so we start with a model, we increase model complexity little by little, we find an optimization technique that can solve that, and in our optimization, we have to tune the optimizer algorithm. There are many different optimizers for neural network, the stochastic gradient descent, atom optimizer, momentum, RMS prop, and so on. And then you can adjust the batch size and learning rate, and all of this have an effect on how fast your model converges. And then as soon as we find the right optimization for this model, we can increase our task complexity, so increasing the data points, the number of data points and labels and size of data points. For instance, if you are dealing with a sequential data, it's better to start with shorter sequences and then increase the length of the sequence and so on. So this gives us a general framework to think about how to approach neural network tuning. So at this point, I'm going to stop. I'm going to go do a quick demo, and then we can do a QA. So everything that we are trying to build at Cluster1 is to enable this kind of systematic work. And here I'm gonna do a quick demo on how to run many experiments and tune find the right hyperparameters for a MNIST example. This is not, I'm not going to go through all the steps that I presented here because we don't have enough time, but I'm happy to answer questions, and later you can message me on our Slack or email or Twitter, and we can discuss in details. So this is a very basic example that we have built, and it's an MNIST model. It's a TensorFlow script that downloads an MNIST example and trains a multi-layer perceptron model. So this model has a few hyperparameters. It's a very basic one. It has the size of, it has 2 hidden layers, and you can adjust the number of units in each of these hidden layers. And then it has a batch size and a learning rate. So these two adjust the complexity of our representation, and these two is for our optimization. And this is a very basic code, so we can look at how to tune this. And I built a basic script here, which is called tune.sh, which will spin up a few jobs that will run this model for different hyperparameters. So I'll adjust my learning rate and then number of nodes in my hidden layer, and I'm gonna try 8 and 64 as the number of nodes in my hidden layer, and different learning rates. So so these are the basic hyperparameters that I'm gonna try, and I'm gonna now just go and run this experiment. So this is I've already created this project here on Cluster1. So you can see this is the demo MNIST that I just created. It's the same files here, so tune.sh, and I'm gonna go launch 6 experiments. So here I just do tune.sh, my username, and then the project name, which is demo MNIST. So what happens now is that we are gonna start 6 different jobs simultaneously, and this will all happen without me having to deal with any infrastructure work. So these experiments are gonna now start running, and within a few minutes I can get a sense about what is the right set of hyperparameters for my problem. So as you can see, these are pending resources, and within a few minutes my experiments are going to start to run. And there are a few tools that are very useful to for debugging in neural networks. One of them is TensorBoard. So with TensorBoard you can visualize various aspects of your training procedure. One of them is that you can visualize any scalar summary. So inside your training procedure, you can emit different summaries. One of them is a scalar. So for instance, you can emit your loss function, your Q size, your accuracy, and so on and so forth. You can emit images or audio, or you can look at your computational graph, and soon we will be able to see all of this. You can emit distributions, so this will help you visualize the distribution of weights in your neural networks, or distribution of gradients. So that helps us understand whether we have, are we seeing vanishing gradients or exploding gradients, for instance. Same with histograms and embeddings and text visualization. So this is an extremely useful tool for debugging and tuning neural network algorithms. And there are tools that helps us tune the neural network systems, which we'll get to in the future sessions. For instance, profiling performance and so on and so forth. So going back to our experiments, let's see. So we are still waiting for the resources. I think I can start answering a few questions until the experiments start running, and then we'll get back to that. Before that, so we'll have a second and third part of the presentation. So the second part of this will be a hands-on tuning for training systems. And I'm going to present how some of the techniques to tune the performance of a neural network training system on your local machine, on Google Cloud and AWS, and on Cluster1. And the same will be for the inference systems, and that's the part 3 of our presentation in the coming weeks, which we will do the same for inference. So with that, I'm gonna pause here and answer a few questions if there are any, and we'll get back to the rest of the demo quickly.
All right. So let me start asking a few questions we collected from the audience. One of them, Mohsen, was about batching. So why do we do batching, and how do you select the correct batch sizes? What are parameters you are looking at when you do that?
Yeah, so yes. So batching. The main algorithm to do optimization for neural network is this gradient descent, and we do usually mini batch gradient descent. And the finding the right parameter for finding the right batch size depends on your system and depends on your algorithm. So generally, if we have larger batch sizes, that means we find more robust gradients, because that gradient comes from having many more batch size, many more instances. But then it comes at the cost of consuming more memory, because during for every instance in our batch, for a forward pass, we have to keep in memory the whole activations for that instance, because we need that for the backward pass. So as you increase the batch size, you increase the memory required for your training. So one of the hard limits of increasing on the batch size is your GPU memory or CPU memory, which you can overcome by going to distributed training, where you can do data parallelism and have generally larger batch sizes by distributing your training onto multiple processors. So the benefit of having a smaller batch size is that you can train faster, and sometimes you can converge faster by exploring more possibilities. And also you can converge sometimes to a better minima, because your model, your optimization can explore a larger space. So there are general rule of thumbs, if for all the standard applications like NLP, vision, and speech, we usually choose a batch size between 64 to 1,000 or a couple of thousand, but it really depends on the optimization algorithm and the computational requirements that we have. It is not the highest priority in terms of optimization. I think you can, the larger the better generally, but that is limited by your computational requirement.
All right, so there was also another question about, is it possible to run distributed TensorFlow on Cluster1? And so the answer is yes. So generally speaking, when you want to run distributed TensorFlow, you need to do a few steps. Number one is changing your code to accept that. And number two is setup. And number three is having the correct infrastructure to orchestrate, track, manage your jobs, and having the correct distributed storage, et cetera, et cetera. So I gave a workshop a few weeks ago about that. That's available on YouTube, and we'll also send it in the webinar that explains how to distribute your code using TensorFlow. But Mohsen, maybe you want to give a brief overview of a few steps required to run distributed TensorFlow?
Yeah, so I can show here in our code actually. So this code is prepared to run in a distributed mode. So this is a TensorFlow, distributed TensorFlow code. What you need to do is do a few minimal changes, which are pretty straightforward. You can also read our blog about that, and the TensorFlow documentation is also relatively nice. And there is also higher level classes that TensorFlow offers, like experiment class that you can use and supports distributed by default. But generally, you just if you want to train distributed on Clusterone, you can change your code such that it accepts parameters that allows it to run distributed. You distribute it over different devices, so you have to define your model in the context of a device, and then you use a monitor training session instead of using the regular sessions. And from there, you can train a distributed one pretty straightforward. You can do just create job, distributed, and then I can do the project. The project is Mohsen demo MNIST, and then module is MNIST, and you can define all the requirements. So I do worker replicas 4 and PS replicas 1, and that should be enough. And now I do just the start job dash. Oh, okay, sorry, I should give it a name. Then we do just the start job, and then the path to that job, which is demo MNIST distributed job. So this will start that job. So it's relatively simple to train distributed jobs on TensorFlow, on Clusterone, as well as Google Cloud ML Engine and AWS SageMaker. But it's becoming harder if you want to train them on your own infrastructure. So this job is now going to provision 4 servers for training this algorithm in a distributed mode on Clusterone. So let's see. So my resources are still pending. Okay, so some of my jobs has started running, and you can see that the model checkpoints are here and the log is here. So let's take a look at that, and this model is converging. So now I can find out what are the better hyperparameters by adding all of my jobs to TensorFlow. So I'm going to add them to TensorFlow, and we'll wait a few seconds, and you can see that these are different jobs. So it will take so the TensorFlow is loading all of my jobs. So you can see, for instance, the job with the learning rate 0, with the learning rate equal to 1, is not doing well. So this is a sign that I can just kill this job immediately. I don't need to wait for another couple of hours until I figure out if this is working or not. So I'm gonna go and kill this job. So learning rate 1 and number of hidden nodes. So I'm gonna just kill that job because it's wasting my money. And similar for the learning rate equal to 1 and the hidden layer 8. So learning rate 1 hidden 8. So as you can see, it's pretty easy to understand what is working and what is not working. And then among the ones that are working, you can see the model with learning rate equal to 0.1 and then 64 nodes in the hidden layer is converging way faster than the model with 8 nodes in the hidden layer. And those models are tend to saturate at some point, so the error won't go down. So this is the point where I know that I can increase my model complexity, and then I'll go to the 64. So this is a quick overview. Maybe I can go back to answering some questions.
So there's a question about how to conduct hyperparameter search. So it sounds like you have this set of hyperparameters you want to try out, and the natural way is to run them sequentially, right? So you check out one hyperparameter, you run an experiment, you look at the results, etc., etc., etc. And if you do that, there starts to be a trade-off between how many combinations you can try and how long you run them, right? So you can run either 10 hyperparameters for 1 hour or one for 10 hours. And so how do you approach that trade-off? What is a good strategy to explore those parameter spaces?
So I think, as we are seeing here, it is usually better to start with a few experiments and hypotheses and kill the ones that are not working, and then from there instantiate new experiments. So I don't think you need to do one experiment for many hours until you figure out if it is working or not. But then the ones that are working, maybe we will need to wait longer to see if they are how they are working. But generally, it's better to run a few experiments in parallel, but not for very long time, until we find the right hypothesis, and then go to the next set of experiments and run them for a little longer. But it's true that you can't know if your model is working necessarily in 1 hour. So this MNIST is a special case where we can see the results so quickly. But generally speaking, it's better to keep your models for many models for a short amount of time, and then find the best ones and let them train for longer, and then prune them as you go. So there are systems that helps you do this automatically. You can also use the softwares that are out there. For instance, you can use softwares that monitor your hyperparameter tuning jobs. ML Engine has some, and SageMaker has some, and Clusterone has some. So that's one of the ways you can do. Oh, okay. Yeah, I have to mute.
So I'll take one or two latest questions, and then we'll close it down and go to the next step. So the next question is about, so there are those different classes of models out there. Some are for vision tasks, some are for text processing tasks. And so is there a different strategy for each class of model, or do you think those things generalize well across classes? Is there one unified approach to treat hyperparameter tuning, or is there an optimal strategy for each model class?
Well, I think I like to emphasize that this approach here to do a coordinate descent optimization is very general. So again, for images, you can start from a smaller number of categories. You can start by smaller images, and all of that to make sure your task is simpler. And then the same for your model, you can make your model simpler. So I think the general strategy is the same. Depending on your task and your model, you may find yourself simplifying or making models or tasks more complicated different ways. For sequential data, you may increase your length of sequence. You may increase the average length of your batch. You may change the complexity of your sequences. For for image it's different. For text, you may start with a smaller dictionary, and then for recurrent neural network models, you may start with less number of recurrent layers and so on. For convolutional neural networks, you can start with less number of layers in your CNN, and so on and so forth. So I think the strategy is generally applicable, but obviously there are rule of thumbs in terms of the starting points, which are quite important. That depends on the task, and really there's a ton of research out there for each of them, but I think this is very general.
All right, so we're reaching the end of this session. So I will just close down by giving some additional resources. And thanks again for asking those questions. Those that we haven't answered, we'll follow up by email and give you pointers if we can. And don't hesitate at all to reach us. I will give you contact information in a second. So we are sending supporting material and invitation to next workshops by email shortly. This video will also be available on YouTube for people who want to share it or watch it again. Don't hesitate at all. Next session, we'll have the privilege to host researcher from Google Brain, Brian Sepasi, who will talk about tensor to tensor. So tensor to tensor is both a framework and a library of models that makes it very easy to build reproducible deep learning research and experiments. And you will give a very hands-on example-based demo of what this tensor to tensor library does. And it's built and developed and used at Google Brain, so it's extremely powerful. And Ryan will give an example of sequence-to-sequence models. So the class of model that includes machine translation or text summarization. So I hope this will be very interesting, and I hope to see you there. Don't hesitate to follow us on Twitter or ping us with questions. We're very active there, and you can reach out to me directly at mel@clusterone.com, and I'll forward the emails to the person that's the most relevant to answer that question. So thanks again for attending, and we hope to see you next time.